we will go to the last speaker of today, which is Marcelo Waimberg from Brazil. He's a designer of structures, and he's also the convener of the task group on precast bridges in the FIB, and he's going to talk to us about this task, these precast bridges.
Thanks, David. I've been following the chat, and I see you have people from good morning through good evening. So hi everybody. I'm making a brief presentation on the last activities of our task group 6.5 on precast concrete bridges. As we are all aware, precast solutions are widely used all around the world, especially for bridges. But if you come to different engineers in different countries and ask them to develop a design for a, let's say, 30-meter long bridge, you probably won't get two solutions alike. And why is that? Well, there are several reasons for that, but mainly because codes largely vary among different countries, practices. This depends also on economic environment, on traditions and culture of each country, availability of equipment, and so on. In view of this, a couple of years ago, Professor Hugo Corres helped installing this task group 6.5 on precast concrete bridges under the Commission 6 of FIB on prefabrication. And the idea was to gather information from examples and experiences from all over the world. And as mentioned early in the morning by our first presentation, to disseminate this information among the engineers community all over the world. This including designers, constructors, and precasters as well. The idea is not to create one or several reports telling what's good, what's better, or what's worse, but rather give information, to disseminate information and experience among the engineers all over the world. So we are not trying to create a single code that everybody should follow, but to share different practices and solutions used everywhere. Our first activities were on the conceptual design itself. And we've almost ready to be published document on the conceptual design process. This document, it explains more or less in a short way how this process should go. And it presents, it's a guidance to conceptual design of bridge superstructures. It can be extended to all kinds of bridges, but it aims on precast girders, bridge superstructures mostly. And what's more interesting in my point of view is that it presents several examples of different solutions following the practice and codes of different countries worldwide. The only constraint that we had for preparing these examples, some of them are real examples, built ones, some of them are theoretical ones, but the only constraint is that they all should cover a 150-meter long bridge with various different aspects depending on the practice of each designer. As I mentioned before, and David also mentioned before, this document is almost ready to be published. In fact, some people that are attending to this webinar have already seen this slide before, telling that it was almost ready, but it takes a while to cover all the bureaucratic issues of publication. So it is almost ready to be published by now. And here you can see some of the you have a touch of what will be found in the document. You have 28 different examples from solutions of boxed girders, I-beam girders, T girders, U girders, with span varying from 15 meter long up to 60 meter long spans. And most of the authors of the document presented, in most cases, 2 or 3 different solutions, varying the length or varying the type of the girder to be used. And here you can find some examples of cross sections used. You have adjacent girders, you have adjacent girders, T-beams, I-beams, girders apart, 2 meters, 3 meters. Here is an example of almost 4 meters apart girders. And the idea is that by learning different solutions and different aspects covered by each of the examples, the designer can internalize these solutions and use creativity in a more creatively way, propose new solutions for new problems that may arise in his day-to-day working life. Even if this is an unconscious process, this is one of the bases of the conceptual design process, to internalize different solutions and to internalize the behavior of these solutions. Here you can find some of each example is extensive and provides calculations and dimensioning of the structure of reinforcing steel, but you will find also a summary of different characteristics of each example. For instance, you will find geometry characteristics such as span length, depth of the girder of the slab for each of the examples. You will also find geometry of the girders, so depth, web width, girder separation, and the precast of each girder proposed, the precast weight of each girder proposed. You will also find information on pre-stress and layout, such as use of strands, tendons, straight ones, rapid ones. You'll find information on the material strength, concrete strength, reinforcing strength, and some information on the structural conceptual design, such as continuity over piers. Sometimes you have no continuity at all with expansion joints. Sometimes you have a linking slab, or you will have sometimes full continuity over the piers. The use or not of diaphragms, especially intermediate ones. We are not telling you, this is a very long discussion. We are not telling you in examples, you should use or you shouldn't use intermediate diaphragms. There are good reasons for using them or for not using them, depending on the constraints you have. in your environment, but we present the difference in the conceptual design using or not these diaphragms. We have a second subject that was focused at first, that is the continuity solutions for these precast girder superstructures, and how to evaluate and how to propose solutions for this continuity. As I mentioned before, we can have no continuity at all with expansion joints. We can have a linking slab between adjacent girders, like in this example. You have here a joint between adjacent girders on the same pier, but you have a linking slab connecting those adjacent spans. And there are several good reasons for using them, but it does not provide real continuity to your structure. And you can have full continuity, like in this example here. You provide this continuity by casting in place the support diaphragm and turning this region in a monolithic joint. You have some here's just a picture showing how to couple. This is just one solution, but to couple reinforcing bars so to provide this continuity. And this report is always very advanced. I wouldn't say it is being published right now, but it is now under review, and it is more or less almost ready to be published. Hopefully we can do it very soon. In this document, you will find some design criteria to evaluate internal forces on the continuity support, as well as in the mid-span. You find criteria to evaluate these internal efforts due to time-dependent effects, such as shrinkage or creep. And we will also find what we'll think it's an important task, examples, real examples of structures that have been built, and we will find in these examples the whole calculation procedure of these internal efforts, as well as the mentioning of precasting, pre-stressing, and mild reinforcement. This is another example you will find there. You will also find different solutions for detailing of reinforcement on this continuity, this continual area made continuous after lifting the girders and by cast in place concrete, with different solutions, especially for the bottom reinforcement, which is always a main concern on how to detail and to develop full strength of especially to bending moments that create tensile stresses on bottom edge of the girder. We have now 3 additional documents that are being carried on. The first of them is on lateral stability of girders. It's been developed by David himself and Albert from Barcelona. And the idea is to provide information and criteria so that designers can evaluate stability of girders but when lifting and moving girders on precast yard or in the industry yard, when moving into the job site, this transportation is an operation that depends on each country regulation, but it's always a point of attention, like transporting these 30 meters, sometimes 40-meter long girders. This is an example of a 35-meter long girder. To check for stability while lifting the girder to the final position. We'll present design criteria for all these checks. And in this design criteria take into account the effect of tolerances, of geometry tolerances or pre-stressing tolerances, and how these affect the safety against lateral stability. And you will find, like in this table here, we'll take in account tolerances for sweep, for camber, eccentricity of pre-stressing forces, or eccentricity of strands or tendons. It depends on each country's practice. You'll find the usual tolerances prescribed by codes in every country, or in some countries that are presented in the test group. Tolerances on the geometry of the lifting devices, on the geometry of the girder, transverse, the cross-section tolerances on its geometry, and so on. And the idea is to prevent examples like this in this picture to happen when you are lifting your girder, for instance, or when you are moving it in a roadway like in this one. And what is I think is a very useful tool. The report will contain also a spreadsheet that you can use for all your checks, but just by inputting your local data, such as codes, tolerances, the geometry of the girder you are designing, the condition that in your country you usually move these girders along roadways, and you can use this input data, and you get the information of how safe you are, or you can even play with some of these inputs and check how changing, for instance, geometry tolerances or geometry of your girder can improve your safety, and so on. We have a second group focused now on precast decks, alternative solutions for these precast slabs. Then we will discuss the convenience or the characteristics of using partially precast slabs against full depth precast elements. Joints between precast elements, especially longitudinal joints between precast panels, how to detail it, different solutions, and criteria to evaluate the strength of these joints. Solutions to connecting these girders, the slab to the girders, such as in this example and in this picture, connecting by stud bolts to steel girders, in fact, in a composite deck, or with using the main stirrup of a concrete girder, connecting with cast in place concrete between the precast elements and the girder. Like in these U-beam here, U-girder here, you can see the stirrups the top face of the girder. And at last, but sure not least, we have a group working on state-of-the-art technology, the use of ultra-high performance concrete for precast bridges. This group is led by Professor Meyer Tadros in the US and Dr. Jackie Vu in Malaysia. And they are developing this document on the use of UHPC. We're talking about, as you've previously heard, in a material with microsilica addition to that mixture, no aggregates, very low water cement ratio, the use of superplasticizers to make these feasible to use, and steel fiber addition. And then we get to, this is a sample of made with this material to be tested. You can see the large amount of steel fibers here in it. And as a result, we have the most thrilling aspects that I think we are now dealing with in our group. You have a very high compression strength material, up to 200 or 250 megapascal. High tensile strength as well, up to 20 megapascal. Very low permeability concrete due to the use of very low water cement ratio and the addition of microsilica, thus leading to a very low shrinkage and creep material, and improving durability, extending the service life of the structure for a large amount. At this point, we really are not interested in exactly evaluating if we are doubling or tripling the service life, but we are aware that it is being extended by a large amount, so that it makes the solution economically feasible. You will also get smaller and much lighter elements, and the icing on the cake, very little reinforcing steel, except for pre-stressing steel. And the report will cover batching, so properties of fresh concrete. We hopefully will provide some guidance on batching this concrete. For sure, properties of the hardened material, design criteria. It's supposed to be a very practice document, so that you will find their design criteria, although this is not a subject covered in many of the codes around the world so far. And again, we will find examples of real bridges that have been built with this material, and how to design and calculate these bridges. This is one of the examples covered by the document. It's a segmental long U-girder, 50-meter long, built with precast segments, and they are all put together by post-tensioning on the job site. This is what the example I never get tired of presenting. Maybe some of you have already seen it. It's a 100-meter long U-girder. It is also built with precast segments, the segments are epoxy jointed over on a steel falsework, and then with post tension they are all put together. And here you can see the U-girder segment at the factory. You have the ducts for post tensioning on the bottom. On the top, you have already the slab connected to the U-girder, and the only reinforcement steel you will find in these segments is small stirrups connecting the top slab to the web of the U-girder. They are very short elements to connect the slab to the girder, and no mild steel reinforcement at all in the elements of this girder, this bridge. Here you can see the elements being assembled over the steel falsework, and here you can find a last example. It's a footbridge that had been built in the Czech Republic. It comprises a 156-meter long central span. This central span was built during a 1-month period, which is amazing. And just to finish this short presentation, I wouldn't like to look like a salesman for UHPC on the use of UHPC, but it's very hard to avoid the thinking of this new material and thinking of the possibilities that the use of this material will bring to the design of concrete structures in general, but in particular to concrete bridges, especially if you take into account the environmental concerns that have been presented in the previous presentations. So we are using a material that have the potential to improve the way we build our concrete structures.
Thank you very much, Marcelo, for this very comprehensive presentation, which gives an overview of how many things are being under development in this group and in previous bridges. It's a lot of things going on. We have a couple questions from Hegadi from India, and he's saying, already there is a publication in FIB on precast segmental construction. Is that going to be covered by DG65 again?
No, we decided to focus on precast girders, mainly because this is the main product that precasters are more used to build around the world. So it does not cover all sort of precasting elements, but rather precast girders. Of course, you will find some issues covered there, but it's mainly focused on precast girders so far.
Okay, and I have a second question from Hagadi. The 100-meter span look like a Bosch girder, not a U girder. He says
well,
it's like a Bosch and not a U girder.
You are right, but he's right. Let me go back there. Am I sharing the screen? Yes, I do.
Yes, yes.
The girder itself is built with these U elements, and then still in the factory, the manufacturer, the precaster, he lays down the precast decks on top of the girder, and then made it monolithic. And then he takes to the job site the whole box completed. You're right, but it's a U girder in the sense that it's being produced as a U girder at once.
Yes. Okay, yes. So yes, it is quite impressive, these new materials. It's a new way of thinking.
Yes, I think we have to get to adjust to it, and it's something that, for instance, here in Brazil, where I am speaking from, we are far away from there at this point. We have lots of research, but as far as I know, we can't produce it yet in an economical way. But I can tell you, and I've been telling this to people here, we have to adjust to that because this is the future of precasting, I guess.
Yes. Well, we can say that these big bridges are from Malaysia, where they develop this technology a lot, and in other countries also, like the United States. After looking at those bridges, they are also having a research program for ultra high performance bridges.
Yes, yeah, that's it.
Okay, as I see no more questions for you, Marcelo. Thank you very much. Thank you for being there since very early in the morning. It was very, very, very interesting.